Hello everyone, welcome to Math 115, College Algebra. In this section, 3.1, we're going to talk about functions, what a function is, and function notation. So the first thing I want to look at is something called a relation. And a relation is simply a set of ordered pairs. So if we look at this example, in example 1 here, let me bring this up a little bit. We have a set, right, represented by the curly brackets here, and then we have several ordered pairs, right? The ordered pairs, so 1, -2, 2, -4, and so on, those are the elements of the set. So that's considered a relation. It's a set of ordered pairs, where the set of all x values, which are the input values. So you can think of for each ordered pair, this first number is the input value, and the second number is the output value. Well, the set of all input values, or x values, is called the domain, and the set of all output values, or the y values, is called the range. So in this case, they're asking for what is the relation's domain and what is the relation's range. So for the domain, we're simply going to list, right, in a set, all of the input values, so all of the x values. So basically, we have 1, right, 2, 4, 7, and 9. So I'll list those. So 1, 2, 4, 7, and 9. So that's the domain, right? It's all the x or input values. I'll write that down here again. So these are all of the x or input values. And the range is going to be all of the y or the output values. So in this case, the range, right, will be a set that contains -2, -4, 0, and then 4. You don't ever repeat, when you write a set, you don't ever repeat values. So even though the 4 is repeated here twice, we only write it once when we write the range, right? We write it in set, as a set. So again, the range is basically all the y or output values. And I'll just remind you, don't repeat values, right? The 4, don't repeat. Okay, so that's sort of like the general case, right? A relation is the most general case. Now, what is a function? Well, a function is sort of a specific type of relation where every element in the domain, right, so the set of all possible inputs, is paired with exactly one element in the range. So the question in this case is that relation that we just talked about in example 1, is that a function? And the answer in this case is yes, and the quickest way to determine that is that the input values don't repeat. Okay, so I'll say yes, and it's because the input values don't repeat. So it is a function. And again, how do I know that? Well, if you look at all these input values, they don't repeat, right? A 1, a 2, a 4, a 7, and 9, they're not repeating. So each input is definitely associated with exactly one output. Now, it could be the same output, that's fine. Like 7 is associated with a 4 and 9 is associated with a 4. Same output is not a problem. It's just that each input has to be associated with exactly one output. So in other words, if we had another ordered pair here that was, say, 7, 2, right? So we have 7, 4, 7, 2. That would not be a function. because now 7 is associated with 2 and 4. But in this case, this is a function, right? So really, we're just looking at the fact that the input values don't repeat. Okay, so I'll kind of summarize that here. So each input value is paired with exactly one output value. Okay, that's what makes it a function. And it's not a problem that the 4 repeats in this case, because the 4, right, was associated with 2 different input values. So I'll just remind you, it's not a problem that the 4 repeats in this case. Right? The input values can't repeat. The output values, it's fine. Okay. There is sort of one special case. Like you could have a case where, let's say the ordered pair was exactly the same. Like let's say we had another 4, 0 and we had another 4, 0 in here. Right? Then technically you wouldn't even, that's why we don't usually repeat things when we write sets. So technically, if you had 2 of them, it's really just 1. So that would still be a function, right? If you have exactly the same input and output values, then you would just write it once and it's still going to be a function. All right, let's do a few more examples of this to make sure we understand what a function is. So this question says, is the relation where you have a numerical score and then a letter grade a function? We're going to assume the numerical score is a whole number, value from 1 to 100, and letter grade is A, B, C, D, or F. So, for example, we could have something like this. I'll just I'll write down a relation here, and we'll see whether it's a function. Let's say I have a numerical grade, and then that corresponds to, say, a letter grade C. Then I have maybe a 90. Let's say that's an A. Then I have, say, a 91, A. Then 92, A, 84, B, and so on. Could have more of them, right? Okay, so in this case, does this relation, it's definitely a relation, right? It's a set of ordered pairs. Does it represent a function? Well, yeah, because the inputs don't repeat, right? 72, 90, these are all distinct. The outputs can repeat, that's fine, but each input is associated with exactly one output, right? The 90 is associated just with the A, the 91 just with an A, 92 just with an A, 84 just with a B. So yes, this is a function. And again, the quick way of saying it is the input values don't repeat. That's the quick way of seeing it. Okay, what about this? So again, I have a relation. And in this case, right, it's a set that consists of an ordered pair where we have a person's name, and their favorite color. So John blue, Mary red, Susan green, Joe blue, Mike red. Is that a function? Well, so the input values in this case are the people, right? Their names. Do they repeat? Nope, they're all distinct, right? John, Mary, Susan, Joe, Mike. And the colors can repeat, that's fine. But each input, each person has exactly one favorite color, right? That's what this is saying. So that is a function. Okay, so I'll say in this case, yes, this is a function because each person has one favorite color. Okay, an example of something that wouldn't be a function, let's say we had this. Let's say we had John Blue then we had Mary Red and then same Mary, we're assuming it's the same person, Green. So in this case, if the input is Mary, there's two outputs, right? I guess Mary has two favorite colors, red and green. So this would not be a function, right? For each input, you can only have one output. So I'll say would not be a function. Okay, in general, so let's talk a little bit about function notation now. In general, we usually name the function f, right? F for function, but other letters are used often as well, like G and H, could be other things as well. But typically we use f. And when you see in the notation f parentheses a close parentheses, you read that as f of a, f of a. And in this case, the a is the input and the f of a, right, is the resulting output. And then again, other letters can be used, right? I would read that as g of x, or I could have h of x, or anything else. Okay, and in these cases, x would be the input, and then g of x would be the output, or x would be the input, and h of x would be the output. Okay, let's do one example where we look at function notation and try to interpret what it means. So let's say we're given the function n is equal to f of y, where n is the number of teachers in a town in year y. Okay, so they're telling us basically that n represents the number of teachers and y represents the year. So let's interpret this. What does the statement f of 2022 equals 300 mean? Well, if you notice here, the input is the year, right? Remember, it's the y, the year. So the input is the year y equals 2022. And then the output is the number of teachers. Which we called capital N, which in this case equals 300. Right? Remember, N is f of y. So in this case, this is like f of y. This is going to be the n, right? The result, the output is the n. All right, so what does this mean? How do you interpret it? You basically say in the year 2022, the town has 300 teachers, right? So in the year 2022, the town has 300 teachers. That's how you would interpret this function notation. Okay, so, and functions can be in many different forms, right? You can have them in word form, you can have them in table form, you can have them in equation form, like algebraic form. We can have them in graph form. So there's many different ways that we can represent functions, and we're going to look at all of these. So let's look at now like the function appearing as a table. So if we look at these tables, there's 5 different examples. We want to determine if those tables represent functions. They certainly represent relations, right? Because I could I could draw a set of ordered pairs, right, based on those tables. But do they represent functions? Well, again, the quickest way to answer that question, let's look at table 1 here. Do the inputs, in this case, the n is the input, the q is the output. So this is basically the input, and the q is the output. Do the inputs repeat? No. 1, 2, 3, 4, 5, right? They're all distinct. So each input corresponds to exactly one output. So yes, this first one is a function. Okay, n doesn't repeat. And if it did repeat, it doesn't have the same output value, right? Because again, if you had exactly the same value for n and q, then that's okay. That would still be a function. Okay, what about the second one? Is this a function? Well, in this case, the age repeats, right? So like several different ages, in this case 5 and 5 are associated with two different outputs, two different heights, right? 5 is associated with a 40, 5 is associated with 42. And also the 8s repeat. 8 is associated with 50, and this 8 is associated with 52. So this is not a function. So you can just say no, and the reason is the age repeats. The input repeats. Right? It's associated with more than one output value. Each input can only be associated with one output value. All right, what about this case? So if the x is the input, the y is the output. All those x values are distinct, right? So this is a function. So I'll say yes, x doesn't repeat. Okay, this example, no, this is not a function, right? Because the -2 is associated with 1, -2 is associated with 3, right? So this particular input, -2, is associated with the two outputs. Just like in this case, this 5 was associated with two outputs, this 8 was associated with two outputs. So this is not a function. So I'll say no, and it's basically because the -2 repeats. And then how about the last one here? Even though all the outputs repeat, right? In fact, they're all the same in this case. It's really, if we're asking whether it's a function, we only care, do the inputs repeat? And in this case, no, the inputs don't repeat, right? Each input is associated with one and only one output. It happens to be the same output, but each input is associated with one output. So yes, this last table represents a function. So the x doesn't repeat, right? It doesn't. We don't care about the y in terms of functions. Later, when we talk about a particular function called a one-to-one function, then we will care about the y as well, the output. But for now, for a function, we only care about does the input repeat. Okay, what about functions in equation form, and how do we evaluate a function when it's in equation form? So let's say we have a function here. So this is like, it turns out it's like a quadratic function, right? Because I have a squared value. The highest exponent here is a 2. My input value is the p, and the output value is h of p. Right, so in this case, the input is p, and the output is the function h of p, which sometimes we give another name, right? You could call it y or something. You could call h of p y. But in this case, we're just leaving it as h of p. So if I want to evaluate that function when p is equal to -4, I literally am going to just plug in -4. Wherever I have a p, I'm going to plug in, substitute in -4. So you can write it like this. So I want h of -4, means p now becomes -4. So where I have a p, I'm going to put in -4. Now you have to be careful, right? Using order of operations correctly. So I have -4 squared means -4 times -4, right? Which is 16. And then 2 times -4 is -8. So this is going to simplify to just 8. So h of negative 4 is 8. Right? When the input is negative 4, the output is 8. Okay, another example of that. Let's say my function is g of m, so the input is m, is the square root of m minus 4, and I want to evaluate g of 5. So that means where I have an m, I'm going to plug in a 5. So this is going to be the square root of 5 minus 4. Well, that's the square root of 1. And I can simplify that. What's the square root of 1? It's just 1, right? 1 squared equals 1. So g of 5 is equal to 1. Okay. The next question. Let's say we're given a relation, right, as an equation, and we want to rewrite it to determine if p is a function of n. So the question here is p a function of n? What that means is you can think of n as the input, and p as the output. So to actually determine this, I want to try and solve the equation for p. And then I can look at it and ask myself, like, for each n, do I get exactly one output? Then it would be a function. So we're going to try and solve this equation for p. Okay, so how do I do that? Well, here, I'll do it over here where I have a little more room. I just want to isolate the p, right? This is really just a linear equation. So I could subtract 12. Let's see. Nope, I want to subtract 2n for both sides. So I'm going to have 6p is equal to negative 2n plus 12. And then I want to divide both sides by 6. Right? So 6's cancel. So I'm going to get p is equal to minus 2n plus 12 over 6. But remember, that's the same as negative 2 over 6n plus 12 over n. And then I can finally write that as p equals negative 1/3 n plus, sorry, this is not an n, this is a 6 here, right? Let me say that again. So negative 2n plus 12 over 6 is negative 2n over 6 plus 12 over 6, right? So this is going to be p equals negative 1/3 n plus, and then 12 over 6 is just 2. So the question is that a function? Yeah, this is just a linear equation, right? In fact, for each n, right, for any value of n, the input that I plug in, I'm going to get exactly one output, right? I'm going to get one p value. If n is 0, p is 2. If n is 3, p, I guess, is 1, right? For each input, you're going to get exactly one output. So yes, this is a function. This is a function. Right? So for each input, for each n, there's exactly one output. Okay, what about this next example? Determine whether the equation x squared plus y squared equals 1 is a function of x. So in this case, again, we're asking, is y a function of x? In other words, x would be the input, y would be the output. So we're going to try and solve this for y, right? So if I try to solve this for y, I need to isolate the y's. So first I'll subtract x squared from both sides. And then I'll just write it as 1 minus. You could write it either as negative x squared plus 1 or 1 minus x squared, same thing. And now to get y by itself, what do I need to do? Well, I need to take the square root of both sides, right? We're basically going to use the square root property. But be careful. Remember, when you do that, you have to account for the fact that it could be positive or negative. So really, we're going to get y equals plus or minus square root of 1 minus x squared. Okay, so is this a function? No. And the reason is for each x, right, for each input of x, I'm going to get two outputs, right? And that it's because of this plus or minus here that's going to lead to two separate outputs. Okay, so that means this is not a function. Here, I'll give you an example. Let's say, we'll do it in blue here. Example, let's say x equals 0, to keep it simple. So if x equals 0, then when we solve for y, we're going to get plus or minus the square root of 1 minus 0 squared, which is plus or minus square root of 1, which is 1. So what this is saying is that if x equals 0, one possibility is y equals negative 1. And if x equals 0, another possibility is y equals positive 1. So this is not a function, right? Because the inputs repeat. For each input, I have more than one output. Okay, so that would not be a function. All right, we're going to look at a table as a function and answer some questions about it. In this next example, example 11 here. So, well, first of all, is this a function? I'm saying it is, but let's double check it. How do we know it's a function? Yeah, if you look at the input values here, the x's, they don't repeat, right? Each x is associated with one output value. Okay, so let's see if we can answer these questions. Evaluate f of 8. Well, this means if 8 is the input, what's the output? Well, the output is going to be 28, right? So in this case, oops, go back there. The 8 here means x is 8, right? Let me do this in black again. So this means x is 8. So if x is 8, that means the output f of 8 is going to correspond to 28 from the table, right? Evaluate f of 0. So this means x is 0. So we go to the table. That means the output is going to correspond to 59. F of 4. So if x is 4, go to the table. That means the output f of 4 corresponds to 47. Okay, what about the last couple? Solve f of x equals 30 for x. Well, this is saying, right, when it says f of x equals 30, it's saying if the output is 30, so we go over here to the f of x now. If f of x is 30, what is the input, right? What's the x value? Well, in this case, x must be 9. Right? Again, you can check it because f of 9 gives me 30. That's why it works, right? If the output f of x is 99, what's the input? Well, in this case, if we look at the table, x must have been 3, right? Which is the same thing as saying f of 3 is equal to 99. Okay, let's look at a little bit now at functions as graphs. So, and I'll talk about this in a second. There's a test to see whether a graph is actually a function or not. It's called the vertical line test, which I'll mention in a minute here. It turns out in this case, this parabola, this is a function, because for each input, right, there's only one output here. So for each input, each x, there's exactly one y value. Okay, let's see if we can answer some questions about this. Well, how would we evaluate f of 0? Well, this is saying the input, if the input is 0, what's the output? So we go to the graph, right? Where we have x equals 0, we want to find the output, so we go up to the graph. In this case, it's equal to 1, right? If the input, if x is 0, the y, the output is 1. So in this case, f of 0 will just be 1. And then the second question says, solve f of x equals 0 for x. So now it's saying if the output, if f of x, if the graph has a value of 0, what's the input? And there could be more than one input, right? But in this case, so it's saying now if f of x, which is the output, is a 0, find the input. Right? There could be more than one answer, but in this case, it's going to be this point right here, right? If the output is a 0, what's the input? Oh, the input is x equals 1, right? Because we know that f of 1 gave us the 0 as an output. Does that make sense? But you could have had more than one answer, right? Let's say here, I'll make up another one. Let's say we want to solve f of x equals 1 for x. In this case, right, the output is 1 here, and the output is 1 here. So in this case, there would be two answers, right? X could be 0, or x could be 2, right? Because in both cases, f of 0 gives me 1, and f of 2 gives me 1. Okay. So again, how do we know, like, what's the quick way to determine whether a graph is actually a function or not? That's when we use the vertical line test. So if I'm going to draw like three different relations, and we'll determine whether they're functions or not. So let's say I'll do one like we just saw. Let's say I'll just do x and y to start. And let's say it does something like this, right, which is what that graph did. Then I'll do, let's say the graph is like linear, so it does something like this. Oops, that wasn't very straight. Goes on forever. And then let's do one more. Let's say I have a graph of like a circle. Let's say it does this. Okay, so in order for a graph to represent a function, then each input has to correspond with exactly one output, right? So the quick way of determining that is do what's called a vertical line test. If a vertical line, and I'll draw a few of them here, only intersects the graph at one place, right? Because I'm saying for each of these inputs, I'm getting exactly one output, right? Just intersecting the graph at one place. If that's true, then the graph represents a function. So let me write that down, and then we'll do the rest of these. So if a vertical line intersects the graph in at most one place, the graph represents a function. Okay, so is the first one? Yeah, certainly this this parabola is a function, right? What about this line here? Yeah, in this case, right, if I do a vertical line test, do a bunch of vertical lines, they only intersect that line in one place. So yes, this is certainly a function as well. What about the circle? So here it doesn't matter because it's not intersecting at all. Here, right at the edge here on both sides, it's just intersecting in one place. But other places, vertical lines are passing through the graph in two places, right? Here and here and here and here. So that does not represent a function. That circle is not a function. Right? It has an equation. You can think of it as a relation, but it's not a function. All right, let's do a little bit more. Let's do one more question example where we answer some. We consider a graph to be a function, and we answer some questions based on that graph. Okay. Actually, first question: is this a function? Yeah, it passes the vertical line test, right? If I draw vertical lines, they only pass through this in one place. By the way, even if you have a graph of just like a few points, let me do something on the side here. Let's say I have like a point here, and a point here, and a point here, and a point here. Would that be a function if I just, had a set of those 4 points listed, right? Those 4 ordered pairs? Yeah. Because it passes the vertical line test, right? Each input has exactly one output. Basically, the x values don't repeat is another way of saying it again. Okay, so based on this graph, question 13, let's see if we can answer these questions. So I want to evaluate f of 2. So now this is saying when x is 2, right, the input is 2, what's the output? Well, if the input is 2, the output is here, right? So it looks like it's going to be 4. So f of 2 is equal to 4. What about f of 3? So this is saying, well, if x is 3, what's the output f of 3? Well, if I go to the graph, go to 3 on the x and go up to the graph, then my output, I guess, is also going to be 3 in this case, right? So f of 3 is equal to 3. What about f of 9 halves? Well, that's saying the input x is 9 halves, which is the same as like 4.5. So if I go to 4.5 here and go up to the graph, what's my output? My output is going to be a 2. Right, so that's just a 2. And then now I want to evaluate f of x equals 1 for x. So now my output is a 1, and I want to find the possible inputs. There could be more than one of them. So I go to the graph, and where is it 1? Actually, it is 1 at a couple of places, right? It's 1 here, and it's 1 here. So there's 2 answers in this case. X could equal 1, or x could equal 7, right? Because the graph is telling us that f of 1 gives me 1, and f of 7 gives me 1. All right. So those are functions, right? Now there's a special type of function which is called a one-to-one function, which is defined here. We're going to talk more about this in a special section later on in chapter 3. And a function is considered to be one-to-one if each output corresponds to exactly one input. So each input has to correspond to exactly one output in order for it to be a function at all, but it'll be a special function, a one-to-one function, if each output corresponds to exactly one input. So that means the inputs and the outputs can't repeat, and then it would be a one-to-one function. And then how do we test this graphically to see whether something is a one-to-one function? Well, if we do the vertical line test, that will tell us whether it's a function, right? If it's not a function, it certainly can't be a one-to-one function. So if it passes the vertical line test, it's definitely a function. Then to determine whether it's a one-to-one function, right, do the outputs repeat? Well, to test that, we can do a horizontal line test. And if it passes both the vertical and the horizontal line test, then it's going to be a one-to-one function. So here, I have some examples on this page. Okay, I want to determine whether these graphs are functions, and then if they are functions, are they one-to-one functions? So let's look at the one on the upper left. So does this, first of all, does it pass the vertical line test? If I draw a bunch of vertical lines, do they just intersect once? Yeah. So this is definitely a function. Does it pass the horizontal line test? No. Actually here, right, it intersects twice. Here it's like an infinite number of times. Twice, here one. But it'd have to just intersect once to be a one-to-one function. So the answer to this one is it's a function, but not one-to-one. Okay, what about the parabola? Is it a function? Yeah, it certainly passes the vertical line test. But then when we do the horizontal line test, nope, it intersects in more than one place at several different locations, right? So again, this is a function, but not one-to-one. Okay, what about the one in the bottom left? Actually, as soon as I go to the vertical line test, it doesn't even pass that, right? It intersects in more than one place. So this is not even a function. So I don't even have to test to see whether it's one-to-one. It's not even a function. What about this cubic? This is going to be a cubic function. So here, yeah, definitely passes the vertical line test. And then if I do the horizontal line test, assuming that it just hits there at one point, yeah, it passes that as well. So this is a function and it's also one-to-one. Now, what about a linear function? Let's say I had something like this. So I have a line. We already know that's a function, right? It passes the vertical line test. Does it also pass the horizontal line test? Yeah. So like a linear function would also be one-to-one. So it's a function and also one-to-one. Or you can just say it's a one-to-one function, right? That implies already that it's a function. So I'll just say it's a one-to-one function. Okay, so you have to pass both the vertical line test and the horizontal line test for it to be a one-to-one function. And then the last couple of pages, it just lists some common functions that you should be familiar with. So I'm just going to show you these and go through them kind of quickly, but you want to be familiar with these. So these are just functions you should be familiar with. So first of all, they're all functions, right? Because they will all pass the vertical line test. So first one is a constant function. What this is basically for each input, there's exactly one output and it's the same output. It's a constant value. So there's a little table here. There's a couple of input values that were given, -2, 0, and 2. And it just so happens the output is always 2 in this case. So when you graph that, you're going to get a horizontal line. So that's a constant function, one that you should be aware of. The identity function says f of x equals x. Right? The constant was f of x equals a constant. In this case, it's 2, but it could be anything, right? F of x equals -3. Then the line would be down here somewhere. It was -3. The next is identity function. Says f of x equals x. So what this says is for each input, you have the same output, right? So -2 is the input, -2 is the output. 0 is the input, 0 is the output. 2 is the input, 2 is the output. And what you get when you plot it is a line like this that passes through the origin, and it has an angle of like 45 degrees. So that's called the identity function. Something you should be familiar with. I'm going to scroll up some. The absolute value function, right? So f of x equals absolute value of x. So if I plug in -2 for x, right, that's my input. When I take the absolute value -2, I'm going to get 2 for my output, right? If I plug in 0 for x, I get 0. If I plug in +2, I still get +2 for the output. If you plot it, it's going to look something like this, right? That's a function you should be familiar with. Quadratic function, which we talked about a little bit before, it has the form f of x equals x squared. So if I plug in some input, I square it, and that will be the output. So -2 times -2 is +4. -1 times -1 is +1, and so on. And that's going to give you a parabola. Let me go back to the upper right. So a cubic function you should also be familiar with. So in this case, right, it has the form f of x equals x cubed. So whatever I plug in, I have to cube the value. So this is, if the input is -1, the output would be -1 times -1 times -1, which is also -1. So that would be this point right here. If the input is -1/2, then the output would be like I guess it's like -1/8, -0.125. It's here. If the input 0, the output 0. So you're going to get this nice cubic function here. You could have a reciprocal function is another common one. So this has the form f of x equals 1 over x. Or you could also write it this way as x to the -1 power. That means the same thing. So again, for each input, so let's say -2 is my input. I plug it in. I'm going to get 1 over -2, which is -1/2, so -0.5. If you plot this, you're going to get this like reciprocal function shape. Reciprocal squared. So now in the denominator, instead of having just x, you have x squared. So f of x equals 1 over x squared. You could also write this as f of x equals x to the -2. Again, if you plug in any input that you plug in, you have to square it, right? So it's going to make it non-negative. And then 1 divided by that will give me the output. So if I plug in -2, I square it, I have 4. And then 1 divided by 4 is a fourth, right? 0.25. So that would be like this value right here, that point right there. And if you do this for a bunch of different inputs, then you're going to get this graph. It has this shape right here. Notice, by the way, that for both the reciprocal function and reciprocal squared function, we cannot plug in 0, right? Because if I plug in 0, I'm going to get something that's undefined. I can't divide by 0 mathematically. So that's why you notice here that there is no output for the 0 here, right? 0 is not in the domain. We're excluding 0. All right, another important function is the square root function. So for this one, and this one is only going to, because we're dealing with real numbers here, right, then I can't have a negative input, right, because there's no real answer for a square root of a negative number. We're not dealing with complex numbers in this case, just real numbers when we graph things. So if I plug in 0, square root of 0 is 0. If I plug in 1, square root of 1 is 1. If I plug in 4, square root of 4 is 2, and so on. And you're going to get this like sideways parabola, which just starts, so the domain is from like 0 to infinity, right, just in this side. And by the way, you can represent square root of x as x to the 1/2, right? You have a fractional exponent. So x to the 1/2 power. And then, let's see, I think there's one more. Oh yeah, the cube root function on the next page. So in this case, this is like the cube root of the input, right? Which I can represent as x to the 1/3 power. So now if the input is -1, I want the cube root of -1. What does that mean? It means what times what times what will give me -1. Well, it turns out -1 actually is the answer here that will work. If the input is a negative, I guess that's like 1/8, then what's the output? So like what times itself would give you -1/8, right? If I say I want f of -1/8, so this is going to be the cube root of -1/8. So the way to think about this is there something when multiplied by itself 3 times gives you -1/8? Yeah, -1/2, right? Times -1/2 times -1/2 is equal to, so negative times negative times negative is negative, 1 times 1 times 1 is 1, and then 2 times 2 times 2 is 8. So if the input is -1/8, the output is -1/2. That'd be that point. And anyways, if you keep going through this, you're going to get this cube root function here, which has this shape. Which actually, by the way, is also 1-to-1, right? Because it passes both the vertical line test and the horizontal line test. Okay, so I'm not going to spend a ton of time, on these toolkit functions, but they are functions that come up all the time, and you really should be aware of them. Okay, next time we're going to talk in more detail about domain and range of functions. Great, thanks.